In this video, we are going to talk about eigenvalues and eigenvectors of 3 by 3 matrices. Okay, in the previous video, we talked about eigenvalues and eigenvectors of 2 by 2 matrices. So let's see how to compute the eigenvalues and the eigenvectors of 3 by 3 matrices. I want to determine the eigenvalues and eigenvectors of this matrix I have here. Okay, before we proceed, in the last video under eigenvalues and eigenvectors, we made use of the equation ax equal to lambda x, from which we said that ax minus lambda x equal to 0. And then if we bring x out, we'll be having a minus lambda I, where I is the identity matrix or the unit matrix, into x equal to 0. And we said that for x not equal to 0, okay, the determinant of a minus lambda I is equal to 0. And we call this the characteristic equation. So we are also going to make use of this to determine the eigenvalues and the eigenvectors of 3 by 3 matrices. All right, let this be the matrix A. So I'm going straight now to determine this characteristic equation. The determinant of this is how to do it in a very simple way. I'll subtract lambda from the numbers on the principal diagonal. These are the elements on the principal diagonal, 2, 3, and 8. I'll subtract lambda from them, and all other numbers remain. So I'll be having 2 minus lambda 7, 0, 1, 3 minus lambda 1, 5, 0, 8 minus lambda. What I have here is equal to what is here. You know, the unit matrix is a 3 by 3 matrix where all numbers on the principal diagonal are 1 and all other numbers being 0. So if we multiply lambda by that identity matrix and subtract the result from this is what we'll get. And this is equal to what? To 0. So we now compute the determinant of this 3 by 3 matrix at the left hand side. Okay, as it is, we have 2 minus 7, 2 minus lambda. 2 minus lambda is positive. Eliminate the row of 2 minus lambda, eliminate the column of 2 minus lambda. We'll have the elements, this, and this. Close up this row, this column rather, and close up this row. What's left is what we're going to put down. This, and this. And the determinant of this matrix, this, and this, is obtained by multiplying this and this minus this and this. 3 minus lambda times 8 minus lambda, all right, minus 0 times 1 is 0. We've done determinant of 3 by 3 matrices already. Is on this channel. You can watch it to understand better. 7 has a place sign of minus. You know, this is plus, minus, plus. So I'm taking minus 7. If I close up this column of 7 and I close up this row of 7, the elements remaining are 1, 1, 5, 8 minus lambda, 1, 1, 5, and this. So the determinant of that matrix is this times this minus this times this. This times this, that's 8 minus lambda. This times this is 5. And lastly, I'll take 0. I'm going to put 0 there. Do you know why? If I multiply 0 by anything, I will still get 0. Yes. If I close up this column of 0 and I close up this row of 0, I'll be having the matrix this, and this. So 0 is going to multiply the determinant of this 2 by 2 matrix, and that will still produce 0. So no need to put it down. just say equal to 0 that we have here. So we now evaluate this. This is 2 minus lambda in brackets, okay, 3 minus lambda, 8 minus lambda. Since this is 0, then we have minus 7 in brackets. This is 8 minus lambda minus 5. 8 minus 5 is 3, then minus lambda equal to 0. I can see 3 minus lambda common to these two terms at the left hand side. So I can bring it out. I'll be having 3 minus lambda. This is left. 2 minus lambda, 8 minus lambda, alright? Then minus 7 is left here, equal to 0. What we are doing now, we are trying to determine the eigenvalues. Values of lambda that we are going to obtain are the eigenvalues. Okay, so we have, let's expand this bracket. 2 times 8 is 16. 2 times minus lambda is minus 2 lambda. This times this is minus 8 lambda. And minus lambda times minus lambda is positive lambda squared minus 7, all equal to 0. Okay, if I simplify that bracket, let me do it here. This is lambda squared. 2 minus 8, that's minus 10. Minus 10 lambda. 16 minus 7 is positive 9. Right? This is it. So I can factorize this. Everything here now is what's here. That is 3 minus lambda in brackets. Lambda squared minus 10 lambda plus 9 equal to 0. This is a quadratic expression. We factorize it to obtain this. Let's do it here again. Two numbers were multiplied to give us 1 times 9, which is 9, and when added to give minus 10. And the numbers are minus 1 and minus 9, because minus 1 times minus 9 is positive 9, minus 1 plus minus 9 is negative 10. Okay, so I'm going to write 3 minus lambda into lambda squared minus, in place of minus 10 lambda, I'm going to write minus lambda minus 9 lambda plus 9 equal to 0. So if we factorize this, we're going to obtain, okay, let's factorize this, let's do it here. This is lambda squared. If I bring it out, I'll be having lambda minus 1. Then if I factorize this last two, minus 9 is common, bring it out, we'll be having lambda minus 1. Okay, so if I rewrite this, I can write it like this now. 3 minus lambda into, I'll pick one of the brackets, lambda minus 1. Then what's outside? Lambda minus 9 equal to 0. And if the product of these numbers at the left hand side equal to 0, it means that 3 minus lambda equal to 0. And okay, let me use comma. Lambda minus 1, no need for brackets, sorry, equal to 0. And this last one, lambda minus 9 equal to 0. And if this is so, from here now, lambda will cross to the other side and become positive. It means that lambda equal to 3. From here, minus 1 will cross and turn to a positive 1. It means that lambda equal to 1. From here, minus 9 will cross and turn to positive 9. It means that lambda equal to positive 9. So let's call this lambda 1, lambda 2, and lambda 3. These are the eigenvalues. So what now are the corresponding eigenvectors? Now, these are the eigenvalues, 3, 1, 9. Alright, this is the matrix, okay? This is the matrix A. For lambda 1 equal to 3, I want to find the corresponding eigenvector of lambda 1, which is 3. So what I'm going to do, I'll subtract 3 from this element here on the principal diagonal. Okay, multiply it by a column vector. A column vector is a matrix that has one column. And of course, this matrix here is going to have 3 rows because we are dealing with 3 rows here also. So we have x1, x2, x3, x1, x2, x3. And the product of this is equal to the 0 matrix, 0, 0, 0. I'm coming from this equation now, this one. This is where I'm coming from, okay? This minus this is minus 1. We have 7, 0. Okay. We have 1, 0, 1. We have 5, 0, 5, right? Multiply by x1, x2, x3 equal to the 0 vector, 0, 0, 0. This vector here, this column vector, is the eigenvector that corresponds to lambda 1 equal to 3. Let's get it. If I expand this by multiplying these two matrices together, I'll be having minus 1 times x1, that's minus x1. 7 times x2, that's 7x2 plus 7x2. 0 times x3 is 0. That's out, and it is equal to what? 0. 1 times x1 is x1. 0 times x2 is 0. 1 times x3 is x3, so I'm having plus x3 equal to 0. Just follow me. 5 times x1 is 5x1. 0 times x2 is 0. 5 times x3 is 5x3 equal to 0. Okay, I have three equations here. Equation 1, equation 2, equation 3. Equation 2 and 3 are the same. The coefficient of x1 here is 1, of x3 here is 1, of x1 here is 5, of x3 here is 5. If I divide all through here by 5, I'm going to obtain what is here. Alright, so 2 and 3 are the same. I can make use of any one. So what I'm going to do now is, from any of equation 2 or 3, I can say x1 equal to negative x3. Right? I'm working with this equation 2 now. Of course, if I reduce this equation 3, I will get this. So let me just use this one to work. x1 equal to negative x3. If x3 cross to the other side, we have minus. Okay. I want to make the coefficient of x1 positive, to be positive 1, and the coefficient of x3 to be positive 1 also. Here is already positive. Okay, so I'm having x1. But this one is negative, so what I will do is I'll bring the minus under. I'm still correct. Yes, I'll bring this minus under as minus 1. This one is the same thing as saying 1. Here, this equation is only in terms of x1 and x3. What about an equation involving x2? That's what I need now. I've gotten an equation that connects x1 and x3. So I need an equation that connects x1 and x2 or x3 and x2. This equation contains x2. So let me make x1 the subject of the formula there, having a denominator of positive 1. x1 here is carrying a plus. It has a denominator of 1. So let me see if I can also write x1 from this equation 2 to be like this. That's what I'm trying to say here. So from that equation 1 now, from equation 1, this is equation 1, minus x1 will be equal to minus 7x2. If 7x2 cross, it turns to minus. x1 here is carrying a minus. Of course, this minus can cancel this minus. We'll be having x1 equal to 7x2. The coefficient of x1 must be positive 1. Here, what is the coefficient of x2 here? 7. Let's make it 1. I can make it 1 by writing it like this: x2 all over 1 over 7. Yes, I think in the previous video I did something like this. See what I'm saying? I have 7 there. To convert 7 to, should I say convert, or to change 7 to 1, is just to multiply it by the reciprocal. 7 is 7 over 1. So if I times it by 1 over 7, I will get 1. That's how I got this. So in fact, s2 all over 1 over 7 means s2 divided by 1 over 7. So if the divide turns to times, it will be x2 times 7 over 1. What would that give? That would give us 7x2 as we have before. So what I did now is to show you that these two, they are the same. So let's proceed. So we have here x1 all over 1. This is x1 over 1. What do I have here? x1 over 1. They are the same thing. They are the same. When you are looking for eigenvalues and eigenvectors using this method I'm using, try to express one variable in terms of the other two. Like in two equations, we express x1 in terms of x3, and this is it. Express s1 again in terms of x2. The eigenvector that corresponds to lambda 1 equal to 3 will now be this. You know, the vector is this vector here, x1, x2, x3. So the vector will now be this. What's x1? What's under x1? Is it not 1? Is 1. It's always 1. So x1 comes first, is 1. What's under x2? 1 over 7. What's under x3? Negative 1. The simplest eigenvector here will be this. I'm having 1 over 7 here, which is a fraction. I can do away with the fraction by multiplying this vector by 7, because this is 1 over 1 minus 1 over 1. 1, 7, 1. The LCM is 7. So multiply everything by 7 to clear off all fractions. We are going to obtain 7. 7 times 1 over 7 is 1. 7 times minus 1 is minus 7. This is the eigenvector that corresponds to lambda 1 equal to 3. It corresponds to lambda 1 equal to 3. The second eigenvalue is 1. That's lambda 2. For lambda 2 equal to 1, I want to cut off a step. So what I'm going to do, you know, when we were calculating for the eigenvector of lambda 1, we used the matrix A and subtracted 3, which is the eigenvalue, from the numbers on the principal diagonal. I want to subtract 1 from the same element here. This is it. This will now be 2 minus 1. 2 minus 1 is 1. I'm having 1 here. I'm having 5 there. 7 is here. 0 is there. 3 minus 1. I'm using this now. That's 2. 0 is there. 1 is there. 8 minus 1. That's 7. I hope you get it. Okay. You can choose to write this matrix, a fresh matrix, and now say 2 minus 1, 7, 0, and all of that. But I want to cut off that step. Then this matrix is multiplied by x1, x2, x3, which is the eigenvector for lambda 2 equal to 1. And this is equal to the 0 matrix, 0, 0, 0. So we now get a system of equations from here. 1 times x1 is x1. 7 times x2 is 7x2. 0 times x3 is 0, equal to 0. 1 times x1 is x1. 2 times x2 is 2x2. Okay, sorry, 2x2. And 1 times x3 is x3, equal to 0. And lastly, 5 times x1 is 5x1. 0 times x2 is 0, that's out. 7 times x3 is 7x3 equal to 0. Okay, so from equation 1 is in terms of x1 and x2. Equation 3 is in terms of x1 and x3. So I can do something like this. From equation 1, from 1, x1 is equal to minus 7x2, right? And so I can say that x1 is, okay, let me write it here. I can say that x1 is equal to x2 all over minus 1 over 7. Do you agree with that? Yes, you agree. That, I think I did that earlier. The minus will come down and the 7 will come down as a reciprocal. So x1 over 1 is equal to x2 all over minus 1 over 7. Let me write an equation that involves x1 and s3. This equation is in terms of x1 and s2. So let me look for an equation that is in terms of x1 and s3, where I will make x1 the subject of the formula. That is, x1 will look like this or like this. You get the point. x1 will be standing alone without any number or any negative sign. From equation 3, we have 5x1 plus 7x3 equal to 0. 5x1 plus 7x3 equal to 0. Okay, which is equivalent to 5x1 equal to negative 7x3. And from this equation, this is 5x1 equal to minus 7x3. Okay, I can just remove the coefficient of x1 from here now by dividing both sides by 5. So I will say x1 equals minus 7x3 all over 5. I need both coefficients to be positive 1. So I can write something like this. x1 equal to x3 divided by, if I'm going to bring this down, it will come down as minus 5 all over 7. I hope you understand that. I've done something similar before. So this is over 1. This is x1 in terms of s3 and this is x1 in terms of s2. So the corresponding eigenvector of this eigenvalue lambda 2 equal to 1 is this. x1 has a denominator of 1, or true. x2 is minus 1 over 7. And x3 is what? Minus 5 over 7. We can do away with the fractions by multiplying through by 7, because 7 is the LCM of all the denominators that we have. So we can say this is 7 times 1 is 7. 7 times this is minus 1. And 7 times this is minus 5. So this is the corresponding eigenvector of lambda 2 equal to 1. I can write this vector in another way. I can represent it in another way. If I multiply this vector by minus 1, okay, I'll be having this minus 7, 1, 5. They are the same thing. An eigenvector can be multiplied by a scalar, a non-zero scalar. Same thing here. We can multiply this vector by minus 1. So if we multiply this vector by minus 1, we'll get the vector minus 7, 1, minus 1, 7. It still corresponds to this eigenvalue. Now, let's determine the eigenvector that corresponds to the last eigenvalue. That's lambda 3. And lambda 3 is equal to 9. For lambda 3 equal to 9, we go straight to the matrix. So as we did earlier, we subtract 9 from the numbers on the principal diagonal. So we're having 2 minus 9, that's minus 7. Then we have 7, 0, 1, 3, 0 is here, 1 is here. 3 minus 9 is minus 6. 8 minus 9 is minus 1. This multiply the corresponding eigenvector x1, x2, x3, and the product is equal to the 0 matrix. This is 5, not 3. Minus 7 times x1 is minus 7x1. 7 times x2 is plus 7x2. 0 times this is 0, that's equal to 0. 1 times x1 is x1. Minus 6 times this is minus 6x2. 1 times this is x3 equal to 0. 5 times x1 is 5x1. 0 times x2, that's 0. This times this is minus x3 equal to 0. From equation 1, okay, we can say that minus 7x1 equal to minus 7x2. Alright, minus 7 will cancel minus 7, and x1 is simply equal to x2, which is the same thing as saying x1 over 1, x2 over 1. Let me now look for an equation that connects x1 and x3 or x2 and x3. This equation 3 connects x1 and x3, so let me just work with that. So from equation 3, I'm having 5x1 equal to x3. The x minus x3 will cross onto a positive x3. So if I remove the 5 from the x1, if I divide both sides, I'll be having x1 over 1 is equal to x3 all over 5, right? So they are both positive, just like we have positive 1 here for both. This is all over 1. So x1, the denominator is always 1. Now, the eigenvector that corresponds to lambda 3 equal to 9 is this. x1 is always 1. x2 has 1. x3 has what? 5. And this vector corresponds to lambda 3 equal to 9. This is it for eigenvalues and eigenvectors of 3 by 3 matrices. Okay, keep supporting by subscribing to this channel, like this video and share it with your friends and your classmates. I'll see you in the next one.